Welcome to this explainer. Today we're taking a profound journey. We're going to explore the mind of Albert Einstein, navigating right through the very fabric of his foundational theories. We'll see how ideas born in a quiet, unassuming office rippled outward, fundamentally altering our understanding of the universe and ultimately changing the course of human history. So we have to begin our journey by asking a pretty staggering question. What actually happens when a single intellect completely shatters our foundational understanding of space, time, and gravity? For over 200 years, the world operated under the strict, absolute rules laid down by Isaac Newton. But the cosmos, as it turns out, is far more deeply intertwined, flexible, and honestly, a lot stranger than anyone had ever imagined. Part 1. The Miracle Year. Byrne Patent Office, 1905. Before the worldwide fame and the iconic hair, Einstein was just a 26-year-old guy. He had a full-time job evaluating patent applications, a young family to feed, and get this, he'd actually been rejected by academia. Yet, in what is now known as his Annus Mirabilis, or Miracle Year, he unleashed 4 revolutionary papers in rapid succession. In March, he proved light acts as both a wave and a particle. In May, the existence of atoms. June brought us special relativity. And in September, E equals mc squared. This was a burst of sheer creativity rivaled only by Isaac Newton's miraculous year back in 1666. This brilliantly illustrates the massive philosophical earthquake Einstein caused. In Newton's universe, time is absolute. It just ticks away objectively, like a giant cosmic grandfather clock, totally unaffected by anything. But Einstein's special relativity reveals a deeply bizarre truth. Time is frame-dependent. Space and time are actually linked together. The faster you move through space, the slower you move through time relative to a stationary observer. Your reality depends entirely on your specific frame of reference.
But Einstein didn't just stop at constant speeds. 10 years later, his scientific journey accelerated into his absolute masterpiece. In 1915, he finalized the general theory of relativity. He proposed that gravity isn't just some invisible magnetic-like pull between two objects, which is what Newton thought. Instead, gravity is the physical curving of space and time itself. Think of it like this. Massive objects sit in the fabric of space-time kind of like a heavy bowling ball resting on a trampoline, literally warping the environment all around them.
Part 2. Warping the Fabric of Reality, the 1919 Solar Eclipse. Now, extraordinary claims require extraordinary evidence, right? So how do you actually prove that the invisible fabric of the universe is bending? Well, in 1919, the world witnessed a nearly 7-minute-long total solar eclipse. When the moon perfectly blocked the sun's glaring light, astronomers could suddenly see the faint stars sitting just behind it. And exactly as Einstein predicted, the sun's immense gravity physically bent the incoming light from those distant stars. Space-time warping was real. And just like that, Einstein became a global icon practically overnight. Part 3. The Ultimate Cosmic Test. Supermassive black holes. So what happens when we take Einstein's math to its absolute, terrifying extreme? NASA supercomputers have actually simulated exactly what Einstein predicted. Imagine a monster supermassive black hole, roughly 4.3 million times the mass of our sun. That is massive. It has an event horizon spanning 16 million miles. Swirling all around it is an accretion disk of hot, glowing gas, and these photon rings made of light that have literally orbited the black hole multiple times. The gravity is so intense it acts like a giant funhouse mirror, heavily distorting and multiplying the starry backdrop of space. Now, the crucial point here is what actually happens if you were to fall into it. It would be a beautifully terrifying 3-hour plunge. To an outside observer watching you, your image would seem to slow down and just freeze forever right on the edge, just shy of the horizon. But for you, you would cross the event horizon, that absolute point of no return, where space-time itself flows inward at the speed of light. Once inside, you'd have just 12.8 seconds before you're stretched in a fatal, frankly gruesome process called spaghettification. Finally, you'd hit the singularity, a point where Einstein's laws of physics simply cease to exist entirely. Part 4. The Warning Letter. Dawn of the Atomic Age. From the awe-inspiring silence of a black hole, we unfortunately have to crash back down to Earth. The very same mind that unlocked the incredible poetry of the cosmos also paved the way for the most destructive force in human history. E equals mc squared was essentially a blueprint for devastating power. In 1938, scientists discovered nuclear fission.
Recognizing the absolutely catastrophic threat if Nazi Germany weaponized this first, Einstein signed an urgent letter to U.S. President Franklin D. Roosevelt in 1939, giving a stark warning that this new phenomenon could lead to bombs of truly unimaginable power.
That single letter set the wheels in motion for the top-secret Manhattan Project. And this is the terrifying realization of that science. The Trinity test fireball, captured just 0.016 seconds after detonation on July 16, 1945, out in a New Mexico desert. The theoretical had abruptly become viscerally, violently real.
Part 5. The Atomic Aftermath. Hiroshima, Nagasaki, and the Historical Debate.
We must now look impartially at the harsh, sobering reality of this historical pivot. The catastrophic power of the atom was about to be unleashed on human populations. Following a final warning that was rejected by Japan, the B-29 bomber Enola Gay dropped the first atomic bomb, known as Little Boy, on Hiroshima on August 6, 1945. Just 3 days later, a second bomb, Fat Man, was dropped on Nagasaki. In a mere instant, over 120,000 people were killed. Infrastructure was utterly crushed, and tragically, thousands more would die in absolute agony from radiation poisoning.
To this very day, historians fiercely debate the decision to use these weapons. On one side, you have scholars like Dr. Peter Zimmerman who argue it was a horrific but necessary shock therapy to prevent a catastrophic land invasion, an invasion that was expected to cost well over 100,000 Allied lives. On the flip side, historians like Gar Oprovips and Tsuyoshi Hasegawa argue the bombs were largely unnecessary for surrender. They suggest it was actually a calculated diplomatic move to intimidate the Soviet Union, and that Japan was already on the verge of surrendering because the Soviets had entered the war.
Regardless of those deeply contested political motivations, the visual evidence of the aftermath is absolutely undeniable. These haunting scars on the Earth profoundly demonstrate the terrible reality of a post-1945 world. We had instantly been thrust into a terrifying new era, a high-stakes Cold War race for nuclear arms that honestly continues to cast a very long shadow over our modern world today.
Which leaves us with a profound, lingering final thought. Einstein's mind brought us the breathtaking beauty of space-time, the terrifying reality of black holes, and the very equation that unlocked the atom. But as human intellect continues to bravely unravel the very fabric of reality, how will we choose to wield the immense, world-breaking power that inevitably comes with it? You see, science gives us the tools to deeply understand the universe, but it is entirely up to us to decide how we use them. Thank you for joining me on this explainer today. I truly hope this journey leaves you looking up at the stars and reflecting on our own world with a completely new perspective.